Welcome to note set number 15, where we continue our discussion of frequency response and start talking about this concept of continuous time filters. We're still talking about continuous time systems here. And basically we've already been talking about continuous time filters. It's just another name for a continuous time system used to modify how much content you have at different frequencies. So we'll continue drilling down on this concept of frequency response like we did in the previous lecture. So lots of times we end up with some input signal that maybe ahead of time we know that there's going to be some range of frequencies that we want and another range of frequencies where there's stuff that we don't want. So the stuff that we don't want we'll consider to be some bad part. And what we want to do is remove that. We want to filter it out. So it's the term comes from like a mesh filter to remove particles from a liquid. Same kind of idea here, except we're removing certain regions of frequency while keeping other regions of frequency. So we've got our system, input signal x of t with Fourier transform x of omega, output signal y of omega with Fourier transform y of omega, and we know that y of omega and x of omega are connected by the system's frequency response. And in this view, when we're trying to use the system to remove certain sections of frequencies, or at least seriously attenuate those, that's when we call it a filter. Not all systems can be considered to be a filter. And we're trying to find out, ideally, what would we like such a filter to look like. So we're going to look at a few cases, by no means exhaustive, not covering all the cases, but setting up some scenarios somewhat idealized so that we can understand why people are seeking these particular types of filters. So suppose we know that we have an input spectrum that looks like this, and there's some frequency omega that above that and then below minus omega, this is a bad part of the signal. We'd like to get rid of that somehow. We'd like to end up with just this part and have it be close to zero, or ideally identically zero out there. So what would we like our system to be able to do in that case? Well, it's pretty obvious from this multiplicative viewpoint, and again, that's the whole beauty of what we've set up here. The whole reason we went through Fourier series and Fourier transforms was so we could get to this point where we say, okay, I know what I want my system to do. I want it to be flat here, and ideally magnitude of 1 there, but it doesn't have to be as long as it's flat. But the important thing is that out here in the bad region, I want it to be 0. And so what this does, if we think about this being high frequencies, these being low frequencies, this passes low frequencies below some cutoff frequency, capital omega. And I use capital omega here, not intending to confuse you with discrete time frequency. Really, I should have used some other symbol there, would probably be a better choice, but well, I've made it and I have to live with it. So this is a filter that passes low frequencies, and not surprisingly, it's called a low pass filter. So mathematically, we would say magnitude of h of omega we want to be equal to 1 in this so-called pass band, and we want it to be 0 outside that pass band, which we'll call the stop band. Okay, case number 2, suppose that the stuff at the low frequencies is the undesired part, and what we want are the stuff at the higher frequencies. So there, what we're going to do is design a filter that passes high frequencies and stops the low frequencies. So above some frequency omega, we pass. Below that frequency omega, we stop. And in that direction as well. So this is, not surprisingly, called a high-pass filter. And we can specify the magnitude of the frequency response accordingly. And again, we have the concept of stop band and pass band. Case number 3, there may be some middle part that is undesired. So, maybe our original signal does something like this, and there's some strong interference in the middle. Well, we can't recover the good part that kind of swoops down there, but we can at least throw out the undesired part that sticks up there. So we will be destroying some of our desired signal, but at the same time getting rid of some really large interference. And so we might design a filter that looks like this, where in some mid-range we are stopping the frequencies, and so this is called a band stop filter. And then it may actually be that this is our desired part, and it's the stuff out here that is not desired. And so now we want to pass this narrow band, and so this is called a band pass filter. Okay, so those are the 4 main categories of filters. By no means is that everything, but those are the main ones that you'll run across. Now, we've been focusing on specifying the magnitude response. What about the phase response? What would we want that to look like? So we'll focus here on the low-pass filter case, but the ideas carry over directly to the other 3 cases as well. So, when we have let's imagine that all we have is our desired signal, and it is completely passed by the say, low-pass filter. So the signal comes out, we want it to look exactly like the original, but we could allow it to have just a small amount of delay, a few milliseconds, maybe even half a second or something like that, depending upon the application. So a small amount of delay would be allowed in most applications. So let's say that X sub G is the good signal. It's completely passed by our system because it lies in our pass band completely. And so the thing that comes out, you might think, well, we would want it to be XG, but we're allowing it to have some amount of delay. So that the amount of delay that we're allowing is this T sub D. So that's what we are saying our ideal filter should be able to provide. And from the time shift property, we know that this delay corresponds to multiplication by e to the minus j omega T sub D, where T sub D is the amount of delay. And so now if we look at what effect that has, well, it doesn't change the magnitude response at all. So in the pass band, the magnitude of this is equal to 1. So our pass band magnitude structure stays the same. But what it does do is the angle of the frequency response becomes the angle of this exponential part, and we see that that is just minus omega sub d TD. We've seen this before. This is the idea of a time shift in a delay in the time domain corresponds to a linear phase shift in the frequency domain. That's what we're seeing here. So to put that together pictorially, here is now our complete specification. T sub D would be some design parameter that we would have to decide what would be an acceptable, allowable delay. But now in our pass band, we want a magnitude of 1 and then a phase that behaves according to this. And then outside of our pass band, we want it to be 0. And so mathematically, we can write that like this, where we're using this rectangular function with a width of 2w as a function of omega to represent this kind of structure. Okay, good. So what can we do with that? Well, not yet. I'm getting ahead of myself here. Here I'm showing the fact that the angle that we're specifying here is this straight line. Okay, so we say that an ideal low-pass filter for that case, any type of filter. An ideal filter is going to have a linear phase in its passband. And so this is just illustrating what it looks like for the low pass case. Now the phase outside of the passband, ideally since it's zero, it doesn't really matter. I mean, what is the angle of zero? What is the angle of a point? Right? It's not pointing in any direction, so it doesn't have any angle. Ideally, we would leave it undefined. We'll see later that in real-world cases, we will have some phases outside of the passband. So to summarize, for ideal filters, our magnitude response needs to be constant in the passband. Doesn't matter really what that constant is. And ideally, we want it to be zero in the stop band. And then the magnitude response, or I'm sorry, the phase response, we want it to be linear in the passband with the slope being equal to the negative of the delay. And in the stop band, we don't really care so much what the phase is. For the ideal case, it's undefined. For real-world filters, we just live with whatever we get. So just to convince you that this linear phase aspect is important, because a lot of engineers think that all they need to do is get a nice magnitude response and that the phase response really doesn't matter. That may be true in some applications, but in other applications it couldn't be more untrue. So let's just look at a simple example. Let's take a look at a simple input signal that consists of 4 sinusoids. Yeah, I know 9 is not necessarily a sinusoid, but we can think of it as a sinusoid at 0 hertz. So one thing at 0 hertz, one at 1 hertz, one at 2 hertz, and one at 3 hertz. And I've constructed a magnitude response here so that at those frequencies, 1, 0, 1, 2, and 3, the filter has a perfectly flat passband at all of those frequencies. So the magnitudes are not being changed at all by this system. And then I'm going to imagine a system whose phase response looks like this. Very non-linear. That's definitely not a straight line in the passband. And see what effect this filter would have on that input signal. Okay, so we know how to modify this. We're going to take each element of our input signal. Its amplitude will stay the same because it's going through the passband, but its phase will be adjusted by whatever these values are. So 9 doesn't get adjusted because it's DC, its phase is 0. But at this frequency, we're going to add, we'll subtract a phase. We'll add like something almost, not quite -1 radians. Then at this frequency, we're going to be adding it looks like it's -pi. I can't remember what I actually put there. And then at this frequency, we'll be adding some small negative amount. And so if we do that, here's what we get. Yeah, okay, so it's -pi/4, -pi, and -pi/10 are these 3 values. So when we do that, the blue curve, we are in the time domain here, so we're looking at the output in the time domain. The blue curve shows that we have this kind of rounded rectangular type or rounded trapezoidal type pulse, which you might expect to find in like a digital communication system, something like that, baseband digital communication system. And the red one is the output. Now, if your digital communication system is looking for a nice rectangular-like or trapezoidal-like pulse, which is what they do, guess what? The red one isn't really looking at all like that. So this simply illustrates that in many applications, the non-ideal phase response can still degrade a signal, even though the magnitude response is perfect. Now, if you were to listen to this example, and I would encourage you to try this, you can create these things. You'll want to use higher frequencies than 1, 2, and 3 hertz. But take that up to, maybe like 1,000 hertz, or maybe 700 hertz, 1,000 hertz, 1,200 hertz, 1,300 hertz. Try that. Don't change the amplitudes, but change the phases, and see what it sounds like both before and after. And my experience shows that there's not a big impact. So what that says is that in the audio world, linear phases tend not to be as important. Now there may be people who will argue with me on that. I'm not an audio engineer. I'm just reporting, some simple little experiments that I've done. But the important thing is that things like communications and radar, areas like that, this linear phase is absolutely crucial. So we've got our wish. We've made our wish. These are what we want, these ideal filters. Can we actually make them? No, we can't. So a big part of what we do as engineers when we're trying to design these things is get close to the ideal. How close can we get, and what resources do we have to use and pay to get as close to the ideal as possible? So let's first of all look at why we can't get such an ideal filter. And the answer is an ideal filter is non-causal. So we've said that this is what we want for our ideal filter frequency response. Let's imagine putting a delta function into this system. So, why that input? Well, I could have used other ones, but a delta function's easy to work with and easy to see. So this delta function's coming along, and what is it doing? The delta function is going to hit the system, boom, right at time equal to 0. And so then we look at what the filter's response has to be. Okay, so let's take a look at that. So what we need to do is we use the fact that x of omega for delta x equal to delta of t is equal to 1. So this goes to 1, so we're left with y of omega is just equal to h of omega, and we've just plugged in what we have there. So now we're going to take the inverse Fourier transform of this to find the output of our system when we hit it with this delta function. Now, also keep in mind that from our Fourier transform properties, we know that this part is just imparting a delay to whatever the inverse Fourier transform of this would be. So if we find the inverse Fourier transform of just that part and then delay it by t sub d seconds, we've got our output. So we go to our table and we discover that there is a term, an entry in the table for this rectangular function in the frequency domain, and it transforms back to a sinc function. So what that tells us then is that our output with a delta function applied at time equal to 0 ends up looking like this. And I've already included the effect of the delay there. So let's look at a picture. Delta function goes into our system at time equal to 0, and what comes out? Well, here's time equal to 0, but look, this thing has already started. How could this system respond to an input that I haven't even put there yet? So it's like the system sitting there saying, I know that this is going to happen at time equal to 0, so I better start wiggling like this because that's what I need to do in response to this delta function. That's just crazy. No real world system can anticipate like that. And so that shows that the ideal low-pass filter, and in fact any of these ideal filters, is going to be a non-causal filter, and we cannot actually build it. So we will have to content ourselves with trying to get as close as possible to that. And one of the things that we'll need to learn about is, well, how do we get close, and what is close and what is good? So let's talk a little bit about plotting the frequency response of practical filters, so that we can get a feeling for how to look at these and visualize them and understand what's good and what's bad. Now, we've been plotting just the magnitude of this in standard numbers versus omega, but it's more common to plot that magnitude in decibels. Now I know what you're saying. Oh wait, those are for measuring how loud a sound is. You hear that, at a rock concert the sound level is, close to 100 decibels. Well, yes, that is used in that setting, but it's a much more general unit than just measuring sound. So let's get the real definition of what a decibel is. It's a logarithmic unit, and it's specifically defined for a ratio between two powers. So when you think decibel, think log ratio powers. Now, originally there was a quantity defined that was called the bell, and then it was found that it was a little easier to work with 10 times that. So 10 times that, in the MKS units, not MKS unit, in the standard, what's the word? I'm totally blanking here. Centimeter, decimeter, that system. I'm totally blanking at this point, a little embarrassing. Multiplying by 10 will turn this into a decibel. So that's why it's called the decibel. So we take 10 log base 10, and then these have to be powers. It's a ratio of two powers. So if we look at this, these values for a bunch of different ratios that are all powers of 10, so if we zoom in on this one here and we say the two powers are equal to each other, that's 0 dB. Okay, so 0 dB is the point where the two powers are the same. Now we're going to be looking at, since h of omega is something that links input to output, the ratios that we'll be mostly concerned with will be the power at the output divided by the power at the input. That's actually what we would be seeing once we get to representing h of omega magnitude in dB. So 0 dB will correspond to no attenuation and no boost. So it's a gain of 1. Now, if our ratio is 10, then we have 10 dB, 100, 20 dB, 1,000, 30 dB. So you can see these go up very fast, but these go up much slower. And it's logarithmic. So the trick is very easy to capture here. It's whatever the power of 3. Well, the logarithm undoes that, so the log base 10 of 10 to the 3 is 3, then we multiply by the 10 and we get 30. So it's very easy to remember these rules. 30 dB is a P ratio of 1,000, 20 dB is 100, 10 dB is 10, 0 dB is 1. And then when we start going to numbers less than 1, ratios less than 1, so when P1 is smaller than P2, then we start getting negative dBs. So negative dBs are attenuation, positive dBs are gain or boost, and 0 dB is no change at all. So these are good rules, and you as a practicing engineer will be expected to know them when you go out for your job interview. Would not surprise me at all if you were quizzed on these kinds of things, and if you're not able to rip them right off in the interview, you might not get that job. And don't think that I'm kidding. Companies are going to be investing a huge amount of money in you over the years. They want to make sure that they're getting something good for their investment. So make sure you learn these things and really know them. And then another rule to know is that when the ratio is 2, we're talking about it's roughly 3 dB. Not exactly, but it's close enough. Everybody just says 3. And when the ratio is a half, it's negative 3 dB. So these are things that you should know. So unfortunately, the frequency response relates voltages, not power. So we need to convert these voltages here. We can see that h of omega is a ratio of the output voltage to the input voltage amplitudes. But what we want is power. So we can convert those into powers for each sinusoidal input by taking a squared over 2 is the power of a sinusoid. Um, and then when we take the ratio, those over 2's go away, the a squareds go away, and we're left with just magnitude squared. So this all boils down to, if we look at a ratio of the output power to the input power, in dB it's 10 log 10 of the square of the magnitude. And then using a property of logarithms, log of a square of something, you take the square out front, so you get 20 log 10. So technically, decibels is defined as 10 log 10 when you're doing ratios of power, but when you're doing ratios of voltage or current or something that's not power, then you do 20 log 10 of the frequency response magnitude. So that's what we'll be using. Now that's another thing that an prospective employer might ask you is, when do you use 20 log 10? When do you use 10 log 10? So you're not just learning these things just to pass the exams and get the degree. You're learning them to go out and do a job, and your employer is going to be expecting you to know these things. So this is what we'll be doing, what we'll be using for our definition for decibels, and when we plot this thing in decibels. Now, the other change that we often make is, we've been plotting on a linear axis where the change is the same increment, right? These are increments of 1,000, but this is a log axis. So notice that these big increments here are multiplicative factors. These are additive factors of 1,000. This is multiplicative factor of 10. Okay, so we go from 10 to the 0 to 10 to the 1, 10 to the 2, 10 to the 4th, and so on. And the main reason that we use a log axis is that it allows us to compress, it allows us to show the frequencies in a way that's more usable to us. So the idea is, well, before I get to that, let me cover this. These internal lines are going up by increments of whatever. I've got this wrong. This should be 2. So this is 10 to the 0, so that's 1. So this should be 2. This is 3, 4, 5, 6, 7, 8. And so on, and then you've got to drop a 0 off from all of these things. So once you get that, the starting line here, you're just taking each multiple of that. So you've got 1, then you go 2, 3, 4, 5, 6, 7, 8, 9, 10, 20, 30, 40, 50, 60, 70, 80, 90, 100, 200, 300, 400, 500, 600, 700, and so on. So that's how we visualize that. But notice that what ends up happening is this 0 to 1,000 range ends up being spread out over a much broader graphical region, and this whole region here gets compressed into just this little bit here. So that's actually helpful for looking at a lot of things like audio frequencies and things like that. Now, we don't always do this, but it's very common to do this. It allows us to look at a broad range of frequencies but not lose some of the important regions. So that's the skinny on all of that. So let's look at an example here. Here's our RC circuit that we've been looking at, and I claim that this is a low-pass filter, and we're going to look at why we say that and what it looks like and compare it to our ideal low-pass filter. So we know how to analyze this using phasor analysis. We convert our capacitor into its impedance value, and we imagine an arbitrary input phasor going in, and then we analyze our circuit to find the output phasor in terms of the input phasor, and the thing that multiplies the input phasor to create the output phasor, that's our frequency response, and it'll be a function of omega. So when we do that, we get something that looks like this, and we declare that this thing that multiplies our input phasor is our frequency response. So there it is. So I've done a little bit of algebra there, and it would be worth your while to go through and replicate that algebra. But there's our frequency response for this RC circuit. And so we can plot that. Here's a plot of it on non-dB scale versus linear axis. And here's some MATLAB commands that I used to plot that. And this is the phase plot, also on a linear frequency axis. And these are correct, and sometimes we might want to look at that. And in fact, we see that yes, indeed, we are attenuating high frequencies, and it looks like we're passing some very small range of frequencies. But it's kind of hard to see what's really going on in there. Everything's all scrunched up. And remember, in audio, most of the significant stuff, even though we can hear up to 20,000 hertz, most of the important stuff that we're hearing is down in this range. So by putting this thing on a log plot helps us a lot. So now we're plotting dB on a log frequency axis. And now we see that, this thing, remember, 0 dB is absolute 1. So this is our nice pass band, and it's staying so beautifully flat all the way up to beyond 100 hertz, and up to 1,000 hertz we've dropped down to 3 dB. Now remember, 3 dB, negative 3 dB corresponded to a power ratio of a half. So when it drops to minus 3 dB, we call that the half power point. That's just a common phrase. So I'll try to write that down here. Minus 3 dB equals half power point. And we'll see later on that that is also called the cutoff frequency of this filter. So we take that minus 3 dB point and view that as this is the stop band, this is the pass band. Even though we're getting some attenuation, again, this is not ideal. So remember, an ideal low-pass filter would be perfectly 0 dB up to our cutoff, and then it would go to, 0 in non-dB. What is that in dB? Minus infinity. All the way down off from the chart. So that's the idea there. And we'll be switching back and forth between dB plots, log axes, non-dB plots, linear axes, whenever is needed. Okay, we'll see you in the next video. Thanks.